Tonight, we're going to confront a problem that should make every atom in your body impossible. Right now, inside every nucleus of every atom that makes up you, positively charged protons are packed so tightly together that the electromagnetic force pushing them apart is enormous. They should explode away from each other. Every nucleus heavier than hydrogen should tear itself to pieces in a fraction of a second. And yet, they don't. Something is overpowering the most familiar force in physics. Something is holding those protons together so firmly that matter itself can exist. And here's what will surprise you. The particle responsible for this isn't the one most people think. It's not the gluon. It's something stranger, something that shouldn't even exist according to early physics. And its discovery changed everything we understand about why matter holds together. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, but probably haven't thought about carefully. You know that protons carry a positive electric charge. You learned that in school. Positive charges repel each other. That's one of the most basic rules of electromagnetism. If you take two magnets and try to push the same poles together, you feel them resisting, pushing apart. That's electromagnetic repulsion. It's the same force, the same fundamental interaction. Positive charges push away from other positive charges. Negative charges push away from other negative charges. This isn't some subtle effect. This isn't a gentle nudge. Electromagnetic repulsion between two protons at nuclear distances is violent. We're talking about protons that are crammed together inside a space that's roughly 1 femtometer across. 1 femtometer. That's 1 quadrillionth of a meter. That's 0.0000000000000000001 meters. To give you some sense of how small that is, if you took a single grain of sand, which is maybe half a millimeter across, and you blew it up to the size of the Earth, a femtometer would still be smaller than your fingertip. The nucleus of an atom exists at a scale so tiny that our everyday intuition completely breaks down. And yet, this is where some of the most powerful forces in the universe are at work. Now, the strength of the electromagnetic repulsion between two charged particles depends on two things. It depends on the amount of charge each particle carries, and it depends on the distance between them. The closer together the charges are, the stronger the repulsion. This relationship is described by Coulomb's law, named after Charles-Augustin de Coulomb, the French physicist who formalized it in 1785. The force between two charges increases as the square of the distance decreases. So, if you halve the distance between two protons, the repulsive force doesn't just double, it quadruples. If you reduce the distance to 1/10, the force increases by a factor of 100. Bring them 1,000th as close, and the force is 1,000,000 times stronger. This inverse square behavior means that forces at very small distances escalate rapidly. At everyday scales, electromagnetic repulsion is manageable. Two charged balloons sitting a meter apart push each other gently, but at nuclear distances, at separations of about 1 femtometer, the electromagnetic repulsion between two protons is staggering. 1 femtometer is roughly 1/1,000,000 of a billionth of the distance between those two balloons. The force doesn't just increase a lot when you shrink the distance that dramatically. It increases by a factor that has 30 zeros after it. If you actually calculate it using Coulomb's law, Plugging in the charge of a proton and a separation of 1 femtometer, the repulsive force between 2 protons sitting that close together is roughly 230 newtons. That might not sound like much in everyday terms. It's about the weight of a medium-sized backpack in Earth's gravity. But remember, this force is acting between 2 particles that are inconceivably small. 2 protons. Each one has a mass of about 1.67 times 10 to the negative 27 kilograms. That's a decimal point followed by 26 zeros and then a 167. These particles weigh nothing essentially by everyday standards, and yet the force pushing them apart is strong enough to lift a backpack off the floor. The acceleration that this force would produce on a single proton if it were free to move is beyond anything in human experience. It's on the order of 10 to the 29th meters per second squared. For perspective, the acceleration due to gravity on Earth's surface is about 9.8 meters per second squared. The repulsive acceleration between 2 protons in a nucleus is roughly 10 billion times stronger than the pull of Earth's gravity. This is the problem. This is the crisis at the heart of every atom. Protons inside a nucleus are close enough to experience this tremendous electromagnetic repulsion. And they don't fly apart. Something is overpowering it. Something is holding them in place. Let's think about what this means for actual atoms. Hydrogen has just 1 proton in its nucleus. No problem there. There's nothing to repel. 1 proton sitting alone doesn't experience any electromagnetic repulsion from other protons because there aren't any other protons. Hydrogen is stable by default, but what about helium? Helium has 2 protons in its nucleus. Those 2 protons are both positively charged, sitting roughly 1 femtometer apart, pushing against each other with about 230 newtons of force. And helium also has 2 neutrons in there, which carry no electric charge and don't contribute to the electromagnetic repulsion. But the neutrons don't shield the protons from each other either. The repulsion is real and it's powerful. And yet, helium is one of the most stable elements in the universe. Helium nuclei are so tightly bound that they're produced in nuclear fusion reactions inside stars. The sun converts about 600 million tons of hydrogen into helium every single second, and it's been doing this for 4.5 billion years. Helium nuclei, once formed, are extraordinarily difficult to break apart. Something is binding them with a force that makes electromagnetic repulsion look weak by comparison. Now go further up the periodic table. Carbon has 6 protons in its nucleus. Oxygen has 8. Iron has 26. Gold has 79. Uranium has 92. Every single one of these elements has multiple protons packed into a tiny nuclear volume, all repelling each other electromagnetically. And the repulsion gets worse as you add more protons. It doesn't just scale linearly. Each new proton you add repels every other proton already in the nucleus. In a uranium nucleus with 92 protons, each proton is being pushed away by 91 other protons simultaneously. The total electromagnetic repulsion energy in a uranium nucleus is enormous, and yet, uranium nuclei exist. They're not perfectly stable. Uranium is radioactive. It does eventually break apart, but it takes billions of years. Uranium-238 has a half-life of about 4.5 billion years, which is roughly the age of the Earth. So even in one of the largest naturally occurring nuclei, the force holding protons together is strong enough to resist that tremendous electromagnetic repulsion for billions of years. Something extraordinarily powerful is at work inside every atomic nucleus. and for decades after the nucleus was discovered, nobody knew what it was. The discovery of the atomic nucleus itself is a story worth telling here because the moment we found the nucleus, we immediately confronted the problem of why it should be impossible. In 1911, Ernest Rutherford, a New Zealand-born physicist working at the University of Manchester in England, conducted one of the most famous experiments in the history of physics. Rutherford directed his colleagues, Hans Geiger and Ernest Marsden, to fire alpha particles at a thin sheet of gold foil. Alpha particles are helium nuclei, 2 protons and 2 neutrons bound together. They're positively charged, and they were being fired at high speed toward the gold atoms. The expectation at the time, based on the prevailing model of the atom proposed by J.J. Thomson, was that the alpha particles would pass straight through the foil with only minor deflections. Thomson's model imagined the atom as a diffuse ball of positive charge with electrons embedded in it, like plums in a pudding. In this model, there was no concentrated mass for the alpha particles to bounce off of. The positive charge was spread throughout the atom, thin and dilute. Most of the alpha particles should sail right through with barely a wobble. It would be like shooting a bullet through fog. The fog is there, but it doesn't have enough concentrated substance to stop anything. And most of the alpha particles did pass through. The overwhelming majority went straight through the gold foil as predicted, detected on a fluorescent screen on the other side. But some of them didn't. A small fraction of the alpha particles bounced back at sharp angles. Some are deflected by more than 90 degrees, and a handful came almost straight back toward the source, as if they had hit something solid and rebounded. Rutherford was stunned. He later described it as the most incredible event of his life. He said it was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Those dramatic deflections could only be explained if the positive charge of the atom wasn't spread out diffusely, but was instead concentrated in a tiny, extremely dense core. A nucleus. The alpha particles that bounce backward were the ones that happened to be aimed almost directly at this dense core. They came close enough to feel the full concentrated electromagnetic repulsion of the nucleus, and were flung back the way they came. Rutherford calculated that this nucleus had to be incredibly small compared to the atom itself. The atom's diameter is roughly 1/10,000,000th of a meter, about 1 angstrom, but the nucleus is roughly 100,000 times smaller than that, about 1 to a few femtometers across. If you scaled an atom up to the size of a football stadium, the nucleus would be a small marble sitting at the center of the field. The rest of the stadium would be empty space with electrons orbiting somewhere in the stands. This was a triumph of experimental physics. Rutherford had discovered the atomic nucleus, but the discovery immediately created a problem that he and everyone else recognized. If the nucleus contains multiple protons, all positively charged, all crammed into this impossibly tiny space, what stops them from flying apart? Electromagnetism says they should repel each other with an enormous force, and at the distances involved, the repulsion is ferocious. Rutherford knew this. Every physicist who understood Coulomb's law knew this. The nucleus shouldn't exist. And yet, it does. Clearly something else was going on. Some other force had to be operating at nuclear distances. A force strong enough to overcome electromagnetic repulsion and bind protons together. But what force? At the time of Rutherford's discovery, physicists knew of only 2 fundamental forces: gravity and electromagnetism. Gravity was immediately ruled out. Gravity is absurdly weak compared to electromagnetism at the scale of subatomic particles. The gravitational attraction between two protons is roughly 10 to the 36th times weaker than their electromagnetic repulsion. That's a 1 followed by 36 zeros times weaker. Gravity is the weakest of all fundamental forces, by an almost incomprehensible margin. At the scale of planets and stars, gravity dominates because large objects contain enormous numbers of atoms, and because matter is mostly electrically neutral, so electromagnetic forces tend to cancel out. But at the scale of individual protons separated by femtometers, gravity is utterly negligible. It contributes nothing to nuclear binding. Less than nothing. It's as if gravity doesn't exist at that scale. So it wasn't gravity. And electromagnetism was the problem, not the solution. There had to be a third force, a new force, something that physicists had never encountered before, something that operated only at extremely short distances. Distances comparable to the size of the nucleus itself, but that was powerful enough to overpower the electromagnetic repulsion between protons. This hypothetical force became known as the strong nuclear force, or sometimes just the nuclear force, and for years it was essentially a placeholder, a name for something physicists knew had to exist but couldn't explain. They could describe some of its properties based on observations of nuclear behavior. They knew it had to be attractive, pulling nucleons together because nuclei are bound systems. They knew it had to be extremely strong, stronger than electromagnetism at short range, because it was clearly winning the tug of war against electromagnetic repulsion inside every stable nucleus. And they knew it had to be short range, meaning it had to essentially disappear at distances much larger than a few femtometers. This last property was absolutely crucial and deeply puzzling. If the nuclear force had the same long range as electromagnetism or gravity, if it extended over large distances with the same kind of slow decline, the universe would look completely different. Every proton in the universe would feel the nuclear attraction of every other proton. All matter might collapse together into one enormous clump. The delicate structures of atoms and molecules and chemistry would be impossible. The nuclear force had to turn on at very close range and then shut off almost completely at slightly larger distances. It had to be like a trap that only works when you're already inside it. Step 2, femtometers away, and you feel an overwhelming pull inward. Step 5, femtometers away, and you feel almost nothing. This was a deeply strange property for a fundamental force to have. This was unlike anything physicists had seen before. Electromagnetism has an infinite range. It weakens with distance, yes, but it never disappears entirely. Gravity has an infinite range too. Both forces weaken with distance, following an inverse square law, but they never fully disappear. You could be a billion light years from a charged particle and still, in principle, feel its electromagnetic influence, however faint. A proton on the far side of the observable universe exerts a gravitational pull on you right now. It's immeasurably tiny, but it's not zero. The nuclear force was different. It seemed to have a hard cutoff. Beyond a certain distance, roughly 2 to 3 femtometers, it just stopped. It vanished. Protons separated by 4 or 5 femtometers behaved as if the nuclear force didn't exist at all. They only felt electromagnetic repulsion. This behavior was new and strange. It demanded an explanation. And the explanation would eventually come, but it would require entirely new physics and entirely new particles that nobody had imagined yet. Through the 1920s and 30s, physicists made progress in mapping the properties of this mysterious nuclear force. The discovery of the neutron by James Chadwick in 1932 was a critical piece of the puzzle. Before Chadwick's discovery, it was unclear what the nucleus was actually made of. Some physicists had proposed that the nucleus contained protons and electrons, with the electrons somehow neutralizing some of the positive charge. But this created serious theoretical problems. Electrons confined to a space as small as the nucleus would have enormous kinetic energy due to the Heisenberg uncertainty principle. The uncertainty principle tells us that the more precisely you confine a particle's position, the more uncertain its momentum becomes. Confine an electron to a space of a few femtometers, and its momentum and therefore its kinetic energy become absurdly large, far more energy than the nucleus was observed to have. The numbers simply didn't work. There were also problems with the nuclear spin. If nuclei were made of protons and electrons, many nuclei would have the wrong total spin based on what was observed experimentally. The neutron solved both of these problems elegantly. The nucleus was made of protons and neutrons, collectively called nucleons. Neutrons had almost the same mass as protons but carried no electric charge, so they didn't add to the electromagnetic repulsion problem. But they did add to the nuclear mass, and they clearly participated in the binding force. In fact, the nuclear force seemed to act between all pairs of nucleons regardless of electric charge. Protons attracted protons, protons attracted neutrons, neutrons attracted neutrons. The force appeared to be roughly the same strength in each case, a property physicists called charge independence. The force didn't care about electric charge at all. This was another crucial clue. Whatever the nuclear force was, it was independent of electromagnetism. It operated on some other property of matter entirely. Some quantum number that protons and neutrons shared, something beyond electric charge, something that physicists hadn't yet identified. But here is where we need to pause and draw a line that is absolutely essential for understanding everything that follows tonight. Because when people hear the term strong force, they often collapse two very different things into one. And that confusion obscures the real story. There are two levels to this force, two distinct layers, and the particle we're going to explore tonight operates at only one of them. The first level is the force that binds quarks together inside a single proton or neutron. Quarks, the fundamental constituents of protons and neutrons, carry a property called color charge. This isn't color in any visual sense. It's a quantum property, like electric charge, but it comes in 3 types instead of 2. Gluons are the particles that carry this force between quarks. They mediate the interaction between color charges, binding quarks together so tightly that no quark has ever been observed in isolation. This is the fundamental strong interaction. It operates inside nucleons, within a single proton or a single neutron. Gluons are the force carriers at this level, and this force has a unique property called confinement. The more you try to pull quarks apart, the stronger the force becomes, until eventually the energy you're putting in creates entirely new particles rather than freeing the quarks. Gluons hold quarks in an unbreakable grip. That's the first level. The second level is the force that binds protons and neutrons together inside a nucleus. This is the force that Rutherford's discovery demanded. The force that holds the nucleus together. And this is not the same force as quark confinement. It's not gluons reaching across from one proton to grab onto another proton. Gluons can't do that. Gluons are confined inside individual nucleons. They cannot escape. A gluon inside a proton cannot leave that proton and travel to a nearby neutron. The color force is locked away, sealed inside each nucleon. The proton as a whole is color neutral. The color charges of the quarks inside it cancel each other out, producing a total color charge of 0. The neutron is the same, color neutral. From the outside, neither proton nor neutron has any net color charge for gluons to interact with. So, the force that holds nucleons together in a nucleus can't be the direct color force mediated by gluons. It has to be something else. Something that leaks out from the internal structure of the nucleon. A residual effect. A leftover. An echo of the deeper force inside. The particle that carries this residual nuclear force, the force between nucleons, is not the gluon. It's something different. And understanding what that particle is, how it works, and why it has the properties it does, is the story we're telling tonight. Think of it this way. Consider 2 atoms of a noble gas, like argon. Each argon atom is electrically neutral. It has the same number of protons and electrons, so its net electric charge is 0. You might think that 2 neutral atoms would have no electromagnetic interaction at all. After all, if the total charge is 0, there's nothing for another charge to push or pull against. And it's true that the dominant electromagnetic forces cancel out. But the electrons and protons inside each atom are not distributed perfectly symmetrically at every instant. Electrons are in constant motion. At any given moment, the electron cloud might be slightly shifted to one side, creating a temporary imbalance, a fleeting asymmetry where one side of the atom is slightly more negative and the other side is slightly more positive. This is called a temporary dipole, and this temporary dipole in one atom creates a tiny electric field that can influence the electron cloud of a nearby atom, inducing a complementary dipole in that neighbor. For a brief instant, the 2 atoms have aligned dipoles that attract each other. Then the electron cloud shift, the dipoles change, but on average over time, there's a net weak attraction. This is the van der Waals force, also called the London dispersion force. It's a residual electromagnetic interaction between electrically neutral objects. It arises because the internal structure of each atom isn't perfectly shielded from the outside at every moment. Something leaks through. The van der Waals force is weak, much weaker than the electromagnetic forces between individual charges inside the atoms. But it's real. It's what allows noble gases to condense into liquids at very low temperatures. Without it, argon could never become liquid argon. Without it, geckos couldn't climb walls. The nuclear force between protons and neutrons works on a similar principle, but at a deeper level. Each nucleon is color neutral, just as each atom is electrically neutral. But the internal color charge distribution within a nucleon isn't perfectly static or perfectly shielded. The quarks and gluons inside are in constant violent motion, a seething quantum storm of interactions. And just as the fluctuating charge distribution inside atoms creates van der Waals forces between them, the fluctuating color charge distribution inside nucleons creates a residual strong force between them. This residual force is what holds the nucleus together. It's not the full strength of the color force. The full color force between quarks is immensely powerful, far stronger than what we observe between nucleons. The residual force is a pale shadow of the force inside, weakened and short-ranged, but still strong enough to overpower electromagnetic repulsion at nuclear distances. And this residual force is carried by a specific particle, not a gluon. Something else. Something that can exist outside of a nucleon, at least briefly. Something with mass, which is what gives the force its short range. That particle is the pion, and its story, from theoretical prediction to experimental discovery, is one of the great triumphs of 20th century physics. But we need to build up to it carefully, because understanding why the pion exists and how it works requires understanding what's happening inside the nucleons that produce it. The essential point to hold in your mind as we go forward is this distinction between two levels of the strong interaction. Inside a nucleon, quarks are bound by gluons through the color force. This is the fundamental strong interaction. Between nucleons, protons and neutrons are bound by pion exchange through the residual strong force. This is the nuclear force that Rutherford's discovery demanded. These are two different phenomena operating at two different scales, mediated by two different particles, gluons on the inside, pions on the outside. The nuclear force that holds your atoms together, that holds every nucleus heavier than hydrogen together, that makes stars burn and planets form and life exist, is not the raw color force between quarks. It's the residual echo of that force, carried by pions, operating at the boundary between nucleons. And the reason this force is short range, the reason it drops to zero beyond a couple of femtometers, has everything to do with the mass of the pion. A massless force carrier like the photon creates a force with infinite range. A massive force carrier creates a force that dies off exponentially with distance. The heavier the carrier, the shorter the range. The pion has mass, and that mass is precisely what makes the nuclear force so localized, so confined to the tiny volume of the nucleus. This is why the nucleus works the way it does. This is why small nuclei are incredibly stable and large nuclei become increasingly fragile. This is why there's a periodic table with the shape it has. This is why some elements undergo radioactive decay and others don't. This is why nuclear fusion powers the sun, and nuclear fission can be harnessed for energy. All of it traces back to the properties of the pion and the residual strong force it mediates. And all of it began with a simple, devastating question asked over a century ago. If protons repel each other, why do nuclei exist? The answer would take decades to assemble, would require the discovery of entirely new particles and entirely new forces, and would reveal that the force holding your body together is not even a fundamental force at all, but the faint residual shadow of something far more powerful, locked away inside the particles that make up every atom you've ever touched. So we've established the problem. Protons inside a nucleus should repel each other with an extraordinary force. They don't. Something holds them together. And we've established that whatever this binding force is, it's not the same thing as the force that holds quarks together inside a single proton. There are two levels, two layers. The deeper layer, the color force between quarks carried by gluons, is locked inside each nucleon. It can't reach out and directly grab a neighboring proton or neutron. The outer layer, the force between nucleons that holds the nucleus together, is something else entirely. It's a residual effect, an echo of what's happening inside. To understand that echo, we need to understand what it's an echo of. We need to go inside the proton. A proton is not a solid ball. It's not a point. It's not a simple thing at all. A proton is a storm. If you could somehow shrink yourself down to the femtometer scale and peer inside a proton, you wouldn't find a calm, orderly structure. You'd find chaos, violent, seething, quantum mechanical chaos. Inside every proton are 3 quarks, 2 up quarks and 1 down quark. These quarks are fundamental particles as far as we know. They have no internal structure. They can't be broken apart into smaller pieces. They are among the most basic building blocks of matter that we've discovered. But the quarks are not sitting quietly inside the proton like marbles in a bag. They're moving at enormous speeds, changing direction constantly, exchanging particles with each other at a furious rate. And those particles they're exchanging are gluons. Gluons are the carriers of the strong force at the quark level. Just as photons carry the electromagnetic force between charged particles, gluons carry the color force between quarks. But gluons are profoundly different from photons in ways that change everything about how the strong force behaves. To understand why, we need to talk about color charge. Electric charge comes in 2 varieties, positive and negative. That's it. 2 types. Opposites attract, as charges repel. Simple enough. Color charge is more complicated. It comes in 3 types, which physicists have labeled red, green, and blue. These names have nothing to do with actual color. You can't see the color charge. It's a quantum property, a label for a type of interaction, nothing more. But the naming convention is useful because it maps onto a rule that mirrors how actual colors work. Just as red light, green light, and blue light combine to produce white light, a combination of 1 red quark, 1 green quark, and 1 blue quark produces a particle with 0 net color charge. This is why protons and neutrons are color neutral. Each one contains 3 quarks, 1 of each color, and the 3 colors cancel out to produce a net charge of 0. This is directly analogous to how an atom with equal numbers of protons and electrons is electrically neutral. The individual charges are there, but they sum to 0. Now here's where gluons become strange. Photons carry the electromagnetic force, but photons themselves are electrically neutral. They don't carry an electric charge. A photon can mediate the force between 2 charged particles, but the photon itself doesn't feel the electromagnetic force. It passes through electric fields without being affected. It doesn't interact with other photons through electromagnetism. This makes the electromagnetic force relatively well behaved. The force carrier doesn't participate in the force it carries. Gluons are different. Gluons themselves carry color charge. A gluon is not color neutral. Each gluon carries 1 color and 1 anti-color. This means that gluons don't just mediate the color force between quarks, they also feel the color forces itself. Gluons interact with other gluons. They attract each other. They can emit and absorb other gluons. This self-interaction of the force carrier is what makes the strong force utterly unlike electromagnetism. It's what creates confinement. It's what makes the color force behave in ways that seem almost impossible from the perspective of our everyday experience with forces. In electromagnetism, the force between 2 charged particles gets weaker as you pull them apart. Move 2 charged objects farther from each other, and the force between them drops. This is intuitive. It matches everyday experience. Hold 2 magnets close together and you feel a strong force. Move them apart and the force fades. The field lines spread out, the force weakens. Everything makes sense. In the strong force, the opposite happens. When 2 quarks are very close together, within about 0.1 femtometers of each other, the force between them is actually relatively weak. The quarks behave almost as if they're free. This property is called asymptotic freedom, and its discovery by David Gross, David Politzer, and Frank Wilczek won them the Nobel Prize in Physics in 2004. It was one of the most important discoveries in particle physics in the second half of the 20th century because it showed that quantum chromodynamics, the theory of the strong force, is mathematically consistent and can make precise predictions at high energies. At very short distances, quarks move around inside the proton with surprising ease. They're bound, but loosely. They have room to maneuver. It's almost as if the cage they're in has very thin bars at closer range. Quarks at very high energies, very close together, behave almost like free particles. You can calculate their interactions using the same perturbative techniques that work so well in electrodynamics. The strong force at short range is, paradoxically, not that strong. But now try to pull those quarks apart. As the distance between two quarks increases, the force between them doesn't decrease, it stays roughly constant, or in some descriptions, it actually increases. This is the opposite of every other force in nature. It's the opposite of gravity. It's the opposite of electromagnetism. Those forces weaken with distance. The color force between quarks strengthens or at least refuses to weaken as you separate them. Why does this happen? Because of gluon self-interaction. When two quarks are connected by a gluon field, that field doesn't spread out in all directions the way an electromagnetic field does. Instead, the gluons attract each other, pulling the field lines together into a narrow tube. Imagine stretching a rubber band between two fingers. As you pull your fingers apart, the rubber band gets thinner and tighter. The force pulling your fingers back together doesn't weaken. If anything, the tension increases the more you stretch. The gluon field between two quarks behaves something like this. As you pull the quarks apart, the gluon field forms a narrow flux tube between them, a string of concentrated energy connecting the two quarks. This flux tube has been observed indirectly through lattice quantum chromodynamics calculations, which are computer simulations of the strong force on a discretized grid of space-time. These simulations confirm that the gluon field between quarks collapses into a tube rather than spreading out. The energy stored in this tube is roughly proportional to its length. The further you pull the quarks apart, the more energy you're pumping into the gluon field between them. The force stays constant or grows because the energy per unit length of the flux tube is approximately constant. Every additional femtometer you stretch, it requires roughly the same amount of energy as the last one. This is radically different from electromagnetism, where the energy between two charges decreases rapidly with distance. What happens if you keep pulling? What if you pump more and more energy into the system, stretching that flux tube further and further? You might expect that eventually you'd pull the quarks apart, that at some point the tube would snap and you'd have two free quarks flying in opposite directions. But that's not what happens. When the energy stored in the flux tube becomes large enough, something extraordinary occurs. The energy converts into mass. Specifically, it converts into a new quark-antiquark pair. The tube doesn't snap to release the existing quarks. It breaks by creating new quarks from the energy stored within it. You end up not with free quarks, but with two new bound systems. Where you had one particle containing quarks, you now have two particles, each still containing quarks bound by gluons. You never get a free quark. Ever. No matter how much energy you put in. No matter how hard you try to pull them apart, the universe simply will not allow a quark to exist alone. The energy you invest in trying to liberate a quark is always redirected into creating new quarks that immediately bind into new composite particles. This is confinement, and it's absolute. In the entire history of experimental physics, with particle accelerators smashing protons together at nearly the speed of light, releasing energies that mimic conditions a fraction of a second after the Big Bang, no one has ever observed an isolated quark. Not once. Not a single free quark has ever been detected in any experiment. In any detector, anywhere on Earth or in space, they always come in groups, always bound, always confined. Physicists at CERN have collided protons at energies of 13 trillion electron volts. They've created temperatures trillions of degrees hotter than the center of the sun. They've momentarily produced states of matter that haven't existed since the universe was a microsecond old. And still, no free quarks. The products of these collisions are always color-neutral composite particles. Quarks bound to antiquarks in pairs are called mesons. Quarks bind to other quarks in groups of 3 called baryons. The confinement principle holds without exception at every energy scale we've ever tested. This has a profound implication for understanding what a proton actually is. A proton isn't just 3 quarks sitting in a box. A proton is 3 quarks embedded in an incredibly energetic gluon field that is constantly producing and reabsorbing virtual quark-antiquark pairs. At any given instant, if you could take a snapshot of the inside of a proton, you wouldn't just see 3 quarks, you'd see those 3 permanent quarks, called valence quarks, plus a swirling chaotic sea of virtual gluons and virtual quark-antiquark pairs that pop into existence and vanish again in unimaginably short spans of time. These virtual particles are called the quark sea and the gluon field, and together they make up most of what a proton actually is. Here's a fact that still surprises people when they first hear it. The 3 valence quarks inside a proton, the up-up-down quarks that define it as a proton, contribute only about 1% of the proton's total mass. 1%. The up quark has a mass of only about 2.2 mega-electron volts, divided by the speed of light squared. The down quark has a mass of about 4.7. Add up the masses of 2 up quarks and 1 down quark, and you get roughly 9.1 mega-electron volts, divided by c squared. But the proton's total mass is about 938 mega-electron volts, divided by c squared. The quarks themselves account for less than 1% of that. So where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the gluon field and the kinetic energy of the quarks as they zip around inside the proton at close to the speed of light. Einstein's equation, E equals mc squared, tells us that energy and mass are equivalent. They're interchangeable. Energy has mass. The tremendous energy contained in the gluon field, the energy of all those gluon interactions, the energy of the quark's rapid motion, the energy of the virtual quark-antiquark pairs constantly flickering in and out of existence, all of that energy has mass. And that mass is the proton's mass. You, right now, are made mostly of protons and neutrons. And those protons and neutrons are made mostly of energy. Not matter in the traditional sense, not solid stuff. Energy. The binding energy of the strong force is expressed as mass through Einstein's most famous equation. Roughly 99% of your body's mass doesn't come from the intrinsic mass of the quarks you're made of. It comes from the force that holds those quarks together. The gluon fields, the kinetic energy, and the ceaseless quantum activity inside every nucleon. You are, in a very real and precise sense, made of force. If you weigh 70 kilograms, about 69.3 kilograms of that is pure binding energy. Less than 1 kilogram comes from the actual rest mass of your quarks. The rest is the strong force made manifest as mass. This is the environment inside every proton and every neutron in the universe. A raging storm of quarks and gluons, virtual particles appearing and disappearing, energy dense beyond comprehension. And all of it is confined, sealed inside a volume roughly 1 femtometer across. The gluons can't leave. The quarks can't leave. The color charge is locked away. From the outside, the proton looks color neutral, quiet, composed. But inside, it's a maelstrom. Now, here's the crucial question. If gluons are confined inside nucleons, if the color charge is sealed away, if protons and neutrons are color neutral from the outside, then how does any force at all leak out between two neighboring nucleons? How does one proton influence a nearby neutron? What mechanism carries the residual strong force between them? Let's think about this carefully, because this is where the two levels of the strong force connect. Inside each nucleon, the quarks are not stationary. They're in constant rapid motion, exchanging gluons furiously. The color charge inside is fluctuating wildly from one instant to the next. At any given moment, the distribution of color charge inside a proton is not perfectly uniform. There are instances where one side of the proton has slightly more color charge influence than the other, just as the electron cloud in an atom can fluctuate and create temporary electric dipoles. But color charge is more complex than electric charge. It comes in 3 types instead of 2. And the fluctuations inside a proton involve not just shifts in the distribution of existing charge, but also the constant creation and annihilation of virtual particles. Among those virtual particles are virtual quark-antiquark pairs, and this is where the story takes a decisive turn. When a virtual quark-antiquark pair pops into existence inside a proton, that pair has specific quantum numbers. It has a specific combination of quark flavor and antiquark flavor, a specific mass range, a specific spin. Under certain conditions, when 2 nucleons are close enough, a virtual quark-antiquark pair in one nucleon can briefly escape the nucleon's boundaries and be absorbed by a neighboring nucleon. This is possible because the pair, unlike a single quark or a single gluon, can be color neutral. A quark and an antiquark can combine to carry a net color charge of 0. And color neutral objects are not confined. Confinement only traps colored objects. Something that is color neutral can, in principle, exist outside of a nucleon. This color-neutral quark-antiquark pair that briefly exists between 2 nucleons is a meson. And the lightest meson, the one most easily produced by these quantum fluctuations, is the pion. The pion is the particle that carries the residual strong force between protons and neutrons. It's a quark-antiquark pair that acts as a messenger between nucleons. It's the particle that makes pion exchange possible, the mechanism by which nucleons attract each other and form stable nuclei. But let's slow down and think about what this means physically. The full color force between quarks is carried by gluons. Gluons carry color charge and are permanently confined inside nucleons. They cannot escape to mediate any force between nucleons. That door is closed. But the quark-gluon system inside each nucleon is so energetic, so dynamic, so full of virtual particle creation and annihilation that it can occasionally produce a color-neutral quark-antiquark pair. This pair is not confined. It can briefly exist between nucleons as a virtual particle. And when it does, it creates a force. This force is the residual strong force, the nuclear force, the thing that holds the nucleus together. It's not the fundamental strong force itself, it's a secondary effect, a spillover, a consequence of the confined system's internal turbulence, producing something that can escape, however briefly, and interact with a neighbor. This is exactly the analogy we explored earlier with the van der Waals force. In that case, the fundamental electromagnetic force between charges inside atoms is mostly cancelled because atoms are electrically neutral. But fluctuations in the charge distribution create temporary dipoles, and those dipoles interact with neighboring atoms, producing a residual electromagnetic force. The nuclear force works the same way, but one level deeper. The fundamental color force between quarks inside nucleons is completely confined, because nucleons are color neutral. But fluctuations in the color charge distribution, manifesting as virtual quark-antiquark pairs, can create color neutral objects that briefly escape the nucleon and interact with neighboring nucleons. The result is a residual strong force, but there's a critical difference between the residual electromagnetic force and the residual strong force. The van der Waals force between atoms is extremely weak. It's much weaker than the electromagnetic forces between individual charges inside those atoms. The residual strong force between nucleons, while weaker than the full color force between quarks, is still extremely powerful. It's powerful enough to overcome the electromagnetic repulsion between protons. It's powerful enough to bind nuclei. It's powerful enough to power stars. The residual strong force is a leftover, yes. An echo, yes. But it's an echo of something so incredibly powerful that even the faint remnant that leaks out is one of the most important forces in the universe. The color force between quarks is the strongest force in nature. Its residual effect between nucleons is weaker, but still strong enough to overpower electromagnetism at short range. Think about what that implies about how strong the original force must be. Electromagnetism is a powerful force. It holds atoms together. It holds molecules together. It's responsible for virtually all of chemistry. It's responsible for the structural integrity of every solid object you've ever touched. And the residual strong force, the pale shadow of the color force, overpowers it easily at nuclear distances. The color force inside the proton is roughly 100 times stronger still. Let's put some numbers on this to make the hierarchy concrete. At a distance of about 1 femtometer, the electromagnetic repulsion between two protons is roughly 230 newtons. The residual strong force between those same two protons at that distance is roughly 20,000 newtons, nearly 100 times stronger. And the color force between two quarks inside a single proton at the same separation is on the order of 100,000 newtons or more, increasing as the quarks are pulled further apart. The hierarchy is clear. The color force is the strongest. The residual strong force is much weaker, but still very powerful. And electromagnetism, which dominates our everyday experience and governs all of chemistry, is the weakest of the three at nuclear distances. This is why nuclei can exist. The residual strong force wins the battle against electromagnetic repulsion. But the residual strong force has a fatal weakness that electromagnetic repulsion doesn't share, and that weakness is range. The residual strong force drops off dramatically with distance. Beyond about 2 to 3 femtometers, it essentially vanishes. This is in stark contrast to electromagnetism, which has an infinite range. The electromagnetic repulsion between two protons never truly disappears, no matter how far apart they are. It weakens, yes. It drops off as 1 over the distance squared, but it never reaches 0. At 10 femtometers, at 100 femtometers, at a meter, at a light year, two protons still repel each other electromagnetically. The residual strong force does no such thing. It operates within a tiny bubble, roughly 1 to 2 femtometers in radius, and outside that bubble, it's gone. This difference in range is the single most important fact about nuclear structure. It determines which nuclei are stable, which are unstable, and how large a nucleus can be before it falls apart. And this short range is a direct consequence of the mass of the pion. A massless force carrier, like the photon, produces a force with infinite range. This is a deep connection in physics. The range of a force mediated by particle exchange is inversely proportional to the mass of the exchange particle. The heavier the carrier, the shorter the range. Photons have 0 mass, so electromagnetism has infinite range. Gluons also have 0 mass, which might seem to predict an infinite range for the color force too. But gluon self-interaction changes the game. Gluons interact with each other so strongly that they can't propagate freely over long distances. The force behaves differently from a simple exchange picture because the carriers themselves are interacting and binding. But for the residual force between nucleons, the carrier is the pion. And the pion has mass, not a lot of mass by everyday standards. The pion's mass is roughly 140 mega-electron-volts divided by c squared, heavier than the electron but far lighter than the proton. We'll look at the exact numbers later when we meet the pion properly. What matters here is that the pion has mass. It's not 0. And because it's not 0, the residual strong force has a finite range. The connection between particle mass and force range is a deep result in quantum field theory, and we'll explore exactly how it works when we reach the physicist who first figured it out. For now, the key fact is this. A massive force carrier can only exist as a virtual particle for a fleeting instant, and in that instant, it can only travel a limited distance. The heavier the carrier, the shorter the distance. For a particle with the mass of the pion, this distance works out to roughly 1 to 1.4 femtometers. Beyond that distance, the pion's influence is exponentially suppressed. The force doesn't just weaken with distance like electromagnetism, it drops off exponentially. It crashes towards 0 far more rapidly than any inverse square law. At 2 femtometers, the pion-mediated force is already a fraction of what it is at 1 femtometer. At 3 femtometers, it's negligible. At 5 femtometers, it might as well not exist. This exponential falloff is described mathematically by what's called a Yukawa potential, named after the physicist who first proposed it, Hideki Yukawa. We'll explore his remarkable prediction in detail shortly. But for now, the essential point is this. The mass of the pion is what makes the nuclear force short range. If the pion were massless, the residual strong force would have infinite range, like electromagnetism. The universe would be a very different place. Nuclei of any size could form. Matter might all clump together. Stars and planets as we know them might not exist. The chemistry that allows life might be impossible. But the pion has mass, and that mass creates a cutoff, a boundary, a limit to how far the nuclear force can reach. And that limit is what gives the periodic table its structure, what determines which elements are stable and which decay, and what sets the maximum size of atomic nuclei. Everything connects. The quarks inside nucleons are bound by gluons through the color force. That force is so strong that it confines quarks permanently. The energy of the gluon field accounts for 99% of the mass of protons and neutrons. The internal turbulence of the quark-gluon system occasionally produces virtual quark-antiquark pairs that are color neutral and can briefly exist outside the nucleon. The lightest such pair forms a pion. The pion mediates the residual strong force between neighboring nucleons. And because the pion has mass, this force is short range, operating only within a few femtometers. This is the mechanism that holds the nucleus together, not gluons reaching between nucleons, not some vague, undefined, strong force. Pion exchange, a specific, well-understood quantum mechanical process in which color-neutral quark-antiquark pairs serve as messengers between nucleons that are close enough to interact. The deeper color force provides the engine, the pion provides the transmission, and together they create the nuclear force that makes atoms heavier than hydrogen possible. That makes chemistry possible. That makes you possible. But this picture, elegant as it is, didn't come easily. It took a brilliant theoretical leap to predict the pion's existence years before it was found. It took a case of mistaken identity that confused physicists for a decade. And it took painstaking experimental work at high altitudes with cosmic rays to finally discover the particle that holds the nucleus together. The story of how the pion was predicted, how it was confused with another particle entirely, and how it was finally identified is one of the great scientific dramas of the 20th century. And it starts with a young Japanese physicist who asked a simple question that nobody else had thought to ask in quite the right way. If the nuclear force has a finite range, what does that tell us about the particle that carries it? The answer to that question would predict the existence of an entirely new particle from pure theoretical reasoning alone, years before any experiment could find it. And it would turn out to be one of the most successful predictions in the history of physics. In 1935, a 28-year-old Japanese physicist named Hideki Yukawa was sitting in his office at Osaka Imperial University thinking about the nucleus. He knew the same facts everyone else knew. Protons and neutrons were bound together, inside nuclei by some force that was stronger than electromagnetism, but only worked at very short distances. He knew that the force had a range of roughly 1 to 2 femtometers, and that beyond that range, it effectively vanished. And he knew that no one had any idea what carried it. But Yukawa had an insight that no one else had put together in quite the right way. He realized that the range of a force tells you something fundamental about the particle that carries it. This was not an obvious connection. To understand why Yukawa's reasoning was so brilliant, you need to understand how forces work at the quantum level. In classical physics, the physics of Newton and Maxwell, forces act through fields. A charged particle creates an electric field that extends through all of space, and another charged particle placed anywhere in that field feels a force. The field is smooth and continuous, stretching to infinity, getting weaker with distance, but never disappearing. This description works beautifully for everyday physics, but at the quantum level, the description changes. In quantum field theory, forces aren't mediated by smooth, continuous fields. They're mediated by the exchange of particles. Two electrons repel each other not because one sits in the other's electric field, but because they exchange virtual photons between them. A virtual photon is emitted by one electron, travels across the intervening space, and is absorbed by the other electron. The momentum carried by the photon is what produces the force. This exchange happens continuously, with enormous numbers of virtual photons being traded back and forth, creating the electromagnetic force we observe. The photon is the force carrier of electromagnetism. It's the particle whose exchange produces the electromagnetic interaction between charged particles. And the photon has a crucial property. It has zero mass. This is not an incidental detail. The masslessness of the photon is directly connected to the infinite range of the electromagnetic force. A massless particle can travel arbitrarily far. There's no energy cost to sending it across any distance. The photon's zero mass means it can mediate interactions between charges separated by any distance, from a femtometer to a billion light years. The force weakens with distance because the virtual photons spread out, but it never fully disappears. This is why electromagnetism has infinite range. The force carrier is massless, so it can reach anywhere. Yukawa's genius was to turn this logic around. He asked the reverse question. If a force has a limited range, if it doesn't extend to infinity but instead cuts off at a specific distance, what does that tell you about the mass of the particle carrying it? And the answer, which he worked out mathematically using the principles of quantum mechanics, was startling. A force with a finite range must be carried by a particle with mass. The reasoning comes from the Heisenberg uncertainty principle, one of the foundational principles of quantum mechanics. The uncertainty principle says that you cannot simultaneously know both the energy and the time duration of a process with perfect precision. There is a fundamental limit. The uncertainty in energy multiplied by the uncertainty in time must be at least as large as the reduced Planck constant, a tiny but non-zero number. This means that energy can be borrowed from the vacuum, so to speak, to create a particle that wouldn't normally be allowed by energy conservation. But the loan has a time limit. The more energy you borrow, the shorter the time you have before you must return it. A virtual particle with high mass requires a lot of energy to create. That energy can only be borrowed for a very short time. During that short time, the particle can only travel a limited distance, even if it moves at close to the speed of light. A heavier virtual particle lives for a shorter time and therefore travels a shorter distance. This means the force it mediates has a shorter range. A lighter virtual particle can exist longer and travel farther, mediating a force with a longer range. And a massless particle, like the photon, can exist indefinitely and travel infinitely far, mediating a force with infinite range. Yukawa did the calculation. He knew the range of the nuclear force was roughly 1 to 2 femtometers. He plugged this into the mathematical relationship between force range and carrier mass. The equation is elegant. The range of a force is approximately equal to the reduced Planck constant divided by the product of the carrier particle's mass and the speed of light. The reduced Planck constant and the speed of light are known constants. The range was measured from nuclear experiments. The only unknown was the mass of the carrier. When Yukawa solved for the mass, he got a value of roughly 200 times the mass of the electron. At the time, the known subatomic particles were the electron, the proton, the neutron, and the positron. None of them had a mass in the range Yukawa was predicting. The proton was about 1,836 times the mass of the electron. The neutron was slightly heavier than the proton. Yukawa was predicting a particle with a mass between the two, heavier than the electron, but lighter than the proton. No such particle had ever been observed. no one had any reason to think such a particle existed. Yukawa was predicting something entirely new, based on pure theoretical reasoning. He was saying that if you accept quantum mechanics, if you accept the uncertainty principle, and if you accept that the nuclear force has a range of about 1 to 2 femtometers, then there must exist a particle with a mass of roughly 200 electron masses that carries this force between nucleons. This was an extraordinary prediction. Yukawa published his theory in 1935 in a paper titled On the Interaction of Elementary Particles. The paper laid out the mathematics clearly. It presented a new type of potential, now called the Yukawa potential, that described a force which decreases exponentially with distance, rather than following the inverse square law of electromagnetism. The Yukawa potential has the form of 1 over the distance multiplied by an exponential decay factor. That exponential decay is what makes the force short range. At distances much smaller than the characteristic range, the force is strong and resembles a standard attractive force. At distances larger than the range, the exponential factor crushes it towards 0. This mathematical form perfectly matched the observed properties of the nuclear force. Strong at short range, negligible at long range, with a smooth transition between the two. Yukawa's paper was revolutionary, but it was published in the Proceedings of the Physico-Mathematical Society of Japan, and initially received little international attention. The physics community in the 1930s was centered in Europe and to some extent the United States. Japanese physics, while producing excellent work, was somewhat isolated from the main currents of Western research. Language barriers and the slower pace of international communication in that era meant that important papers could take months or even years to reach the wider scientific community. Yukawa's prediction sat quietly in the literature, a brilliant idea waiting for experimental confirmation that would vindicate everything he had proposed. And then, in 1936, something happened that seemed to confirm it. Carl Anderson and Seth Neddermeyer, working at the California Institute of Technology, were studying cosmic rays using a cloud chamber, a device that reveals the path of charged particles as trails of tiny droplets. They found a new particle. It had a mass between that of the electron and the proton. It seemed to be almost exactly what Yukawa had predicted. Physicists were excited. The nuclear force carrier appeared to have been found. This new particle was initially called the mesotron, later shortened to meson, meaning middle particle, because its mass was in the middle range between electron and proton. It seemed like a perfect match. But there was a problem. As physicists studied this new particle more carefully, it didn't behave the way Yukawa's theory said it should. Yukawa's predicted particle was supposed to interact strongly with nucleons. That was its entire purpose. It was the carrier of the nuclear force. It should stick to protons and neutrons. It should be absorbed by nuclear matter readily. When it passes through matter, it should interact frequently and be captured by nuclei. The particle Anderson and Neddermeyer found did none of these things. It passed through matter almost without interacting. It could penetrate deep into the Earth's atmosphere, traveling through enormous amounts of air and even through solid materials without being absorbed. This was completely wrong for a nuclear force carrier. A particle that carries the strongest short-range force in nature should be gobbled up by nuclei almost instantly. It shouldn't be able to sail through matter as if the nuclei weren't there. The Italian physicist Marcello Conversi, along with Ettore Pancini and Oreste Piccioni, performed a decisive experiment in 1947 in Rome, working in remarkably difficult conditions in the aftermath of World War II. They studied what happened when these cosmic ray particles stopped in matter, comparing their behavior in materials of different atomic numbers. If the particles were Yukawa's predicted nuclear force carriers, they should be quickly captured by nearby nuclei when they came to rest. What Converse's team found was that the particles stopped in matter and then simply decayed on their own without being captured by nuclei. This was definitive. The particle discovered by Anderson and Neddermeyer was not Yukawa's meson. It was something else entirely. Something that looks superficially similar because it had approximately the right mass, but that had completely different interaction properties. This particle, which we now call the muon, turned out to be a heavier cousin of the electron. It's a lepton, a particle that does not feel the strong force at all. It interacts only through the electromagnetic force and the weak force. The muon has absolutely nothing to do with nuclear binding. Its discovery in cosmic rays at roughly the mass Yukawa predicted was a cosmic coincidence, a cruel trick of nature that sent physicists down the wrong path for over a decade. The physicist I. Rabi, upon learning that the muon was not the predicted nuclear force carrier, but instead a pointless-seeming, heavier copy of the electron, famously asked, "Who ordered that?" It was a question born of genuine frustration. The muon seemed to serve no purpose. It didn't fit into any existing theoretical framework. It was just there, an unexplained duplicate of the electron with no obvious role in the structure of matter. And the real nuclear force carrier was still missing, but not for long. The true pion was discovered later in 1947, the same year as Converse's experiment, by Cecil Powell and his team at the University of Bristol in England. Powell used a different experimental technique from cloud chambers. He used photographic emulsions, special thick photographic plates, coated with silver halide crystals that could record the tracks of charged particles passing through them with extraordinary spatial resolution. A charged particle moving through the emulsion would ionize atoms along its path, creating a trail of exposed silver grains that became visible when the emulsion was developed, much like a conventional photograph. These emulsions were carried to high altitudes in the Pyrenees Mountains and in the Andes Mountains and on high-altitude balloon flights, where cosmic rays are more intense, because they haven't been filtered by as much atmosphere. When Powell's team developed the emulsions, they found something striking. They could see tracks of particles that entered the emulsion and then stopped. At the point where these particles stopped, they could see a second particle emerging and continuing on. This was a particle decaying into another particle. The first particle, the one that stopped, interacted strongly with the nuclear material in the emulsion. It was readily absorbed by nuclei. When it entered a nucleus, it caused the nucleus to disintegrate, blowing it apart in a burst of nuclear fragments. This was exactly the behavior Yukawa had predicted for the nuclear force carrier. Strong interaction with nuclei, ready absorption, violent nuclear reactions upon capture. The second particle, the one that emerged from the decay, was the muon. The true picture finally became clear. Cosmic rays produce pions in the upper atmosphere. These pions, if they didn't hit a nucleus first, decayed into muons. The muons, being leptons that don't feel the strong force, then penetrated deep into the atmosphere and were what Anderson and Neddermeyer had originally detected on the ground. The confusion had lasted over a decade. two different particles, one that interacted strongly with nuclei and one that didn't, both with similar masses, both produced in cosmic ray interactions. It took careful experimental work to disentangle them and identify which was the true nuclear force carrier. Powell was awarded the Nobel Prize in Physics in 1950 for his development of the photographic emulsion technique and his discovery of the pion. Yukawa had already received the Nobel Prize in 1949 for his theoretical prediction of the meson, making him the first Japanese citizen to receive a Nobel Prize. The prediction and discovery of the pion was one of the great triumphs of 20th century physics. A particle predicted purely from theoretical reasoning, based on the range of a force and the principles of quantum mechanics, was found to exist exactly as predicted. It confirmed that the quantum mechanical picture of forces as particle exchange was correct, and it opened the door to the modern understanding of nuclear structure. Now let's look at what the pion actually is. We know from the modern quark model that pions are not fundamental particles. They're composite. Each pion is made of a quark and an antiquark, bound together by the color force. There are three types of pions, distinguished by their electric charge. The pi plus has an electric charge of +1. It's made of an up quark and an anti-down quark. The up quark carries a charge of +2/3, the anti-down quark carries a charge of +1/3, and together they add up to +1. The pi minus has an electric charge of -1. It's the antiparticle of the pi plus. It's made of a down quark and an anti-up quark. The down quark carries a charge of -1/3. The anti-up quark carries a charge of -2/3, and together they give -1. The pi zero is electrically neutral. Its quark content is more subtle. It's a quantum mechanical superposition of an up quark paired with an anti-up quark and a down quark paired with an anti-down quark. It doesn't have a single definite quark composition at any given moment. It exists in a blend of both possibilities simultaneously, which is characteristic of quantum mechanics. The charged pions, pi plus and pi minus, have a mass of about 139.6 mega-electron-volts divided by c squared. That's about 273 times the electron's mass, close to Yukawa's original estimate of roughly 200 electron masses. The neutral pion is slightly lighter at about 135 mega-electron-volts divided by c squared. These masses are what determine the range of the nuclear force. The charged pions live for about 26 nanoseconds before decaying, predominantly into a muon and a muon neutrino. The neutral pion lives for a spectacularly short time, about 84 attoseconds. That's 84 billionths of a billionth of a second. It decays almost instantly into 2 photons, 2 gamma rays that fly apart in opposite directions. These lifetimes might seem impossibly brief, but they're actually long compared to the timescales on which virtual pion exchange operates inside a nucleus. Now, let's understand the exchange mechanism itself, because this is the core of how the nuclear force actually works. Imagine a proton and a neutron sitting near each other inside a nucleus, separated by about 1 femtometer. The proton is a churning quantum system of quarks and gluons. Among the constant creation and annihilation of virtual particles inside the proton, a virtual quark-antiquark pair can form that constitutes a pion. This virtual pion is not a real particle in the usual sense. It doesn't satisfy the normal relationship between energy and momentum that real particles obey. It's a quantum fluctuation, a temporary borrowing of energy allowed by the uncertainty principle. This virtual pion leaves the proton and travels the short distance to the nearby neutron. The neutron absorbs it. The force between the proton and neutron arises from this exchange, just as the electromagnetic force between two electrons arises from photon exchange. But something remarkable can happen during this exchange that doesn't happen in electromagnetism. The pion can carry an electric charge. If the proton emits a pi plus, it loses 1 unit of positive charge. The proton, which has a charge +1, becomes a neutron, which has a charge 0. The pi plus travels to the nearby neutron. The neutron absorbs the pi plus, gaining 1 unit of positive charge, and becomes a proton. The two nucleons have swapped identities. What was a proton is now a neutron, and what was a neutron is now a proton. This process is called charge exchange, and it's a fundamental feature of the nuclear force that has no analog in electromagnetism. When two electrons exchange a photon, they remain electrons. The photon is neutral. It doesn't change the identity of the particles that exchange it, but pions can be charged. A charged pion exchange transforms a proton into a neutron, and a neutron into a proton simultaneously. This charge exchange has profound implications. It means that inside a nucleus, the identity of any particular nucleon is not fixed. A nucleon that is a proton at one moment might become a neutron the next, and vice versa, as charged pions are exchanged back and forth. The nucleus is not a static collection of protons and neutrons with fixed identities. It's a dynamic system where nucleon identities fluctuate constantly through pion exchange. This is one reason why the nuclear force treats protons and neutrons almost identically. From the perspective of the strong force, protons and neutrons are nearly interchangeable. They're two states of the same particle, the nucleon, related to each other by pion exchange. This symmetry between protons and neutrons is called isospin symmetry, and it's an approximate symmetry of the strong force that played a crucial role in the development of nuclear physics and eventually in the development of the quark model. Neutral pion exchange also occurs. A proton can emit a pi 0 and remain a proton. A neutron can emit a pi 0 and remain a neutron. In neutral pion exchange, no identity change. The pi 0 simply carries force between the two nucleons without altering their charges. All three types of pion exchange contribute to the nuclear force. The total force between two nucleons is the sum of contributions from charged and neutral pion exchange. And the character of the force, whether it's attractive or repulsive, depends on the specific quantum states of the nucleons involved, their relative spins, their isospin orientations, and the type of pion being exchanged. It's essential to emphasize something here that often gets lost in simplified explanations. The pions exchanged between nucleons are not real particles sitting inside the proton waiting to be thrown at a neutron. They're virtual particles. They don't exist before the exchange begins, and they don't exist after the exchange ends. They exist only during the exchange, for an unimaginably brief period of time, and only because the uncertainty principle allows temporary violations of energy conservation. A virtual pion doesn't travel through space the way a bullet travels from a gun. It's better understood as a quantum mechanical process, a mathematical contribution to the interaction between two nucleons that can be visualized as particle exchange, but is really a feature of the underlying quantum field. The language of particle exchange is a useful picture, and it gives the right answers when you calculate with it, but the virtual pion is not a little ball flying between protons and neutrons. It's a disturbance in the pion field, a quantum fluctuation that connects two nucleons and creates a force between them. The same caveat applies to virtual photons in electromagnetism. When we say two electrons exchange virtual photons, we don't mean actual photons are flying back and forth like tiny tennis balls. We mean that the quantum mechanical calculation of the force between two electrons can be organized as a sum over contributions from virtual photon exchanges. Each contribution corresponds to a Feynman diagram, a pictorial representation of a term in the calculation. The simplest diagram shows a single photon exchanged between two electrons. More complex diagrams show 2 photons, 3 photons, photons that produce and reabsorb virtual electron-positron pairs along the way, and so on. The force is the sum of all these contributions. For electromagnetism, the simplest diagrams dominate, and the corrections from more complex diagrams are small. For the strong force, the situation is more complicated, because the force is so strong that the corrections from complex diagrams are not small. This makes calculations of the nuclear force from first principles extremely difficult. Now let's bring this all together and note what we've built. We now have a complete chain of causation running from the deepest level of matter up to the structure of the nucleus. The color force confines quarks inside nucleons and generates almost all of their mass. The confined quark-gluon system, through its internal quantum turbulence, produces virtual pions that can briefly escape because they are color neutral. These virtual pions create an attractive force between neighboring nucleons, and the pion's mass ensures that this force operates only within a range of 1 to 2 femtometers, dropping off exponentially beyond that. Each link in this chain depends on the one below it, and each link involves different physics. Remove any link and the chain breaks entirely. No color force means no nucleons. No pion exchange means no nuclei. No nuclei means no atoms heavier than hydrogen. The mechanism is layered, precise, and beautiful, and the pion sits at its center, the critical messenger that translates the confined violence inside nucleons into the binding force that holds nuclei together. What makes this picture so satisfying is how cleanly the two levels separate. The color force and the nuclear force are related, but they are not the same thing. One operates inside nucleons and is carried by gluons. The other operates between nucleons and is carried by pions. Most popular descriptions collapse them into a single entity called the strong force, as if it were one thing doing one job. It's not. It's 2 distinct mechanisms operating at 2 distinct scales, connected by the fact that the second is a residual consequence of the first. Recognizing this distinction is essential. Without it, you cannot understand why the nuclear force has the range it has, why it has the strength it has, or why it produces the specific pattern of nuclear stability that gives rise to the periodic table. And the key to this entire mechanism, the particle that makes it all work, is the pion. Without the pion, there would be no bridge between nucleons. Gluons are confined. They can't cross the gap. But pions, being color neutral, can. They're the smallest, lightest package that the quark-gluon system inside a nucleon can produce that is allowed to exist outside the nucleon's boundary. They are the minimum viable messenger between 2 nucleons, and their mass, roughly 140 megaelectronvolts, is not arbitrary. It's determined by the dynamics of the color force, by the masses of the up and down quarks, and by the mechanism of chiral symmetry breaking in quantum chromodynamics. The pion's mass sets the range of the nuclear force, and the range of the nuclear force determines which nuclei can exist and which cannot. It determines the structure of the periodic table, the energy output of stars, the formation of the elements, and ultimately the existence of every complex structure in the universe, from planets to proteins to people. Everything depends on pion exchange, and pion exchange depends on the deeper quark-gluon dynamics that we've explored. The hierarchy of forces, from the confined color interaction inside nucleons to the residual pion-mediated interaction between nucleons, to the electromagnetic repulsion that the nuclear force must overcome, is the architecture that holds matter together. But so far we've described how this architecture works in principle. We haven't yet explored its consequences. We haven't asked what the pion's specific properties, its mass, its range, its strength, actually produce when you build nuclei out of real protons and real neutrons. The answer to that question is the periodic table itself, and the story of why some nuclei last forever while others fall apart in an instant. So now we have all the pieces. We know that protons repel each other electromagnetically with tremendous force at nuclear distances. We know that the force holding them together is the residual strong force, a secondary effect of the deeper color force between quarks. We know that this residual force is mediated by pion exchange, virtual quark-antiquark pairs that briefly exist between neighboring nucleons. And we know that because pions have mass, this force is short range, dropping off exponentially beyond about 1 to 2 femtometers. Now we need to put all of this together and understand what it actually means for the structure of matter. Because the interplay between pion-mediated attraction and electromagnetic repulsion doesn't just determine whether nuclei exist, it determines which nuclei exist. It determines the shape of the periodic table. It determines why stars burn the way they do. It determines why some elements are stable forever and others fall apart in fractions of a second. And ultimately, it determines why you are here. Let's start with the simplest case. A single proton, hydrogen, 1 proton, no neutrons. There's no electromagnetic repulsion because there's only one charged particle. There's no need for the nuclear force because there's nothing to bind. Hydrogen just exists. It's the simplest and most abundant element in the universe, making up roughly 75% of all normal matter by mass. Hydrogen fills the vast clouds of gas between stars. It fuels the fusion reactions in stellar cores. It's the raw material from which everything else is built. And it requires no nuclear force to hold it together because it's just 1 proton with nothing to repel and nothing to bind. Now add 1 neutron. You get deuterium, an isotope of hydrogen with 1 proton and 1 neutron. This is the first nucleus that actually requires the nuclear force to exist. The proton and neutron are close enough for pion exchange to operate. Virtual pions pass between them, creating an attractive force that holds them together as a bound pair. There's no electromagnetic repulsion between them, because the neutron is electrically neutral. Only 1 proton means no proton-proton repulsion to fight against. The pion-mediated attraction holds them together unopposed. Deuterium is bound, though not very tightly. Its binding energy is only about 2.2 mega electron volts. That's relatively modest by nuclear standards. It means deuterium can be broken apart by a sufficiently energetic photon, a gamma ray with energy above 2.2 mega electron volts. But under normal conditions, deuterium is perfectly stable, Now add another proton and another neutron. You get helium-4. 2 protons, 2 neutrons. This is where things get interesting. You now have 2 protons, and those 2 protons repel each other electromagnetically. But you also have 4 nucleons, all of which can exchange pions with each other. The proton-proton pair exchanges pions. The neutron-neutron pair exchanges pions. Each proton-neutron pair exchanges pions. There are 6 possible pairs among 4 nucleons, and the pion-mediated attraction operates between all of them. The result is that helium-4 is extraordinarily tightly bound. Its binding energy is about 28.3 mega-electron-volts, roughly 7 mega-electron-volts per nucleon. This is remarkably high for such a small nucleus, far above anything else in the light element region of the periodic table. Helium-4 is so stable that it's practically indestructible under normal conditions. It takes extreme temperatures, the kind found in the cores of massive stars, to break it apart. This exceptional stability is why helium-4 nuclei, also called alpha particles, are emitted intact during many forms of radioactive decay. When heavy, unstable nuclei shed mass, they often eject a complete helium-4 nucleus rather than individual protons or neutrons, because the helium-4 nucleus is such a tightly bound, energetically favorable package. As you continue adding nucleons, something remarkable happens to the binding energy per nucleon. It increases, not just for helium, but continuing upward through the periodic table. Lithium, carbon, nitrogen, oxygen, each successive element tends to have a slightly higher binding energy per nucleon than the one before it. The nuclear force is winning. Each nucleon you add gets to exchange pions with several neighbors, and the cumulative attraction grows. The binding energy per nucleon climbs from about 1 mega-electron-volt for deuterium to about 7 for helium, to about 7.7 for carbon, to about 8.0 for oxygen. The nuclei are getting more tightly bound as they get bigger. More nucleons mean more pion exchange partners, which means more total attraction. But this trend doesn't continue forever. It peaks. The most tightly bound nuclei in the universe, the nuclei with the highest binding energy per nucleon, are iron and nickel. Specifically, iron 56 and nickel 62 are the most tightly bound nuclei known. Iron 56 has a binding energy of about 8.79 mega-electron-volts per nucleon. Nickel 62 is slightly higher at about 8.795. These are the champions, the most stable configurations of nuclear matter that exist. And after iron and nickel, the binding energy per nucleon starts to decrease. Slowly at first, then more noticeably as nuclei get larger. By the time you reach uranium with 92 protons and 146 neutrons, the binding energy per nucleon has dropped to about 7.6. Still bound, still stable enough to exist for billions of years, but less tightly bound than iron. Why does the binding energy peak at iron and then decline? This is where the short range of the pion-mediated force collides with the long range of electromagnetic repulsion, and the consequences are profound. The nuclear force mediated by pion exchange is short range. Each nucleon can only interact with its immediate neighbors, the nucleons within about 1 to 2 femtometers. In a small nucleus like helium or carbon, this isn't a problem because every nucleon is close to every other nucleon. The nucleus is so small that every nucleon is within range of every other one. They all exchange pions with each other. They're all pulling on each other. The binding is efficient. But as nuclei get larger, this changes. In a large nucleus, nucleons on one side are too far away from nucleons on the other side for pion exchange to operate between them. A proton sitting on the left edge of a uranium nucleus is separated from a proton on the right edge by roughly 15 femtometers, far beyond the 1 to 2 femtometer range of the pion-mediated force. Those two protons don't attract each other through pion exchange. They can't. The force simply doesn't reach that far. Each nucleon in a large nucleus interacts only with its nearest neighbors, perhaps 10 or 12 other nucleons in its immediate vicinity, not with all the nucleons in the nucleus. This means that as you keep adding nucleons to a growing nucleus, there's a diminishing return. Each new nucleon you add gets attracted to a fixed number of nearby neighbors, maybe 12 or so. The attractive contribution per nucleon levels off. It doesn't keep increasing because the new nucleon can't reach nucleons on the far side of the nucleus. The pion-mediated attraction saturates. It reaches a maximum per nucleon contribution and stays roughly constant no matter how many more nucleons you add. But electromagnetic repulsion doesn't saturate. Electromagnetism has an infinite range. Every proton in the nucleus repels every other proton in the nucleus, regardless of distance. A proton on the left side of a uranium nucleus repels a proton on the right side, 15 femtometers away. The force is weaker than it would be at 1 femtometer, of course, because of the inverse square law. But it's not zero. It's never zero. And critically, every new proton you add to a growing nucleus repels all the protons already there, not just the nearby ones. The total electromagnetic repulsion energy in a nucleus grows with every proton you add. It scales roughly as the total number of proton pairs in the nucleus, which grows as the square of the number of protons. Double the number of protons and the total repulsive energy roughly quadruples. Triple the protons and the repulsion grows roughly 9-fold. This quadratic growth is relentless. For small nuclei, it's manageable. For large nuclei, it becomes overwhelming. So the competition is between a short-range attraction that saturates and a long-range repulsion that doesn't. For small nuclei, the attraction wins easily because every nucleon is within pion exchange range of every other nucleon, and there aren't many protons to create repulsion. For medium-sized nuclei around iron and nickel, the two forces are in optimal balance. The nucleus is large enough to benefit from lots of pion exchange, but small enough that the growing electromagnetic repulsion hasn't yet overwhelmed the attraction. This is why iron sits at the peak of the binding energy curve. It's the sweet spot. For nuclei larger than iron, the electromagnetic repulsion starts to gain ground. Each new proton adds repulsion with every existing proton, but only attraction with its nearest dozen neighbors. The balance tips. The binding energy per nucleon begins to decline. The nucleus becomes progressively less tightly bound. This is why nuclear fusion releases energy for elements lighter than iron, and nuclear fission releases energy for elements heavier than iron. In fusion, you take small nuclei and combine them into larger ones. If the product nucleus is more tightly bound than the reactants, which it is for everything up to iron, the excess binding energy is released. This is what powers the sun. Hydrogen nuclei fuse into helium, releasing energy because helium is more tightly bound than hydrogen. The mass of the helium nucleus is measurably less than the combined mass of the 4 protons that went into making it. That missing mass, about 0.7% of the original mass, has been converted into energy according to Einstein's equation E equals mc squared. Every second, the sun converts about 4 million tons of matter into pure energy through fusion. It has been doing this for 4.5 billion years, and will continue for roughly another 5 billion. And all of this energy, every photon of sunlight that has ever warmed your face, traces back to the difference in pion-mediated binding between hydrogen and helium. In massive stars, fusion continues beyond helium. Helium fuses into carbon and oxygen. Carbon fuses into neon and magnesium. Oxygen fuses into silicon and sulfur. And silicon fuses into iron. Each step releases energy because each product is more tightly bound than its inputs. But at iron, the process stops. Fusing iron into heavier elements would require energy input rather than producing energy output, because heavier nuclei are less tightly bound than iron. The star has climbed the binding energy curve to its peak, and can go no further. When a massive star accumulates an iron core, fusion ceases. The core loses its energy source. Gravity, which has been held at bay by the outward pressure from fusion energy, suddenly wins. The core collapses in on itself in a fraction of a second. Temperatures soar to hundreds of billions of degrees. Densities reach levels comparable to the density inside a proton itself. The core is compressed until the nucleons are practically touching, packed so tightly that the short-range repulsive core of the nuclear force, the hard inner wall that prevents nucleons from overlapping, finally halts the collapse. The infalling material rebounds off this incredibly dense core, sending a shock wave outward that tears the star apart in a supernova explosion. For a few weeks, a single dying star becomes bright enough to be seen across the entire observable universe, rivaling the combined light of billions of ordinary stars. In the extreme conditions of the supernova, with temperatures and pressures far beyond anything in normal stellar cores, elements heavier than iron are forged. Gold, platinum, uranium, all the heavy elements that exist on Earth were created in supernovae or in neutron star collisions, events so energetic that they could force nuclei past the iron peak and build heavier elements despite the energy cost. Every gold atom in every ring and necklace on Earth was forged in the death throes of a star or in the violent merger of two neutron stars. And the reason those gold nuclei hold together, the reason they survive the journey from stellar explosion to planet formation to the jewelry on your hand is pion exchange. Nuclear fission works in the opposite direction. You take a heavy nucleus, one that sits on the declining side of the binding energy curve, and you split it into smaller pieces. If those smaller pieces are more tightly bound than the original heavy nucleus, which they are for very heavy elements, the excess binding energy is released. This is what happens in a nuclear reactor. Uranium-235 absorbs a neutron and splits into two medium-sized nuclei, typically something like barium and krypton, plus a few free neutrons. The products are more tightly bound than the uranium, so energy is released. About 200 mega electron volts per fission event. This energy ultimately comes from the difference in pion-mediated binding between uranium and its fission products. Every nuclear reactor on Earth, every nuclear weapon ever detonated, draws its energy from the interplay between the short-range pion-mediated attraction and the long-range electromagnetic repulsion inside heavy nuclei. The declining binding energy for nuclei heavier than iron also explains radioactive decay. Nuclei that are too large, that have too many protons and too many neutrons, are progressively less stable. The electromagnetic repulsion is constantly trying to tear them apart, and the pion-mediated attraction is doing its best to hold them together, but the balance is precarious. These nuclei exist in a constant state of tension, like a structure that is bearing more load than it was designed to carry. Some of these nuclei are metastable. They exist in a state that is energetically unfavorable, but protected by an energy barrier that the nucleus must tunnel through to decay. Quantum mechanical tunneling is one of the strangest features of the quantum world. A particle that classically doesn't have enough energy to cross a barrier can nevertheless appear on the other side of that barrier with a small but non-zero probability. It's as if you threw a ball at a wall and occasionally the ball just passed through. In the nuclear context, an alpha particle inside a heavy nucleus doesn't have enough kinetic energy to escape the nuclear potential well. But quantum mechanics allows it to tunnel through the barrier with some probability. This probability is small for heavy nuclei with high barriers, which is why many radioactive isotopes have long half-lives. Uranium-238 has a half-life of 4.5 billion years, not because it's particularly stable, but because the energy barrier it must tunnel through is high enough that the probability of tunneling in any given moment is extremely small. But eventually, given enough time, it will decay. Every radioactive element heavier than lead will eventually decay, shedding protons and neutrons until it reaches a configuration where the pion-mediated attraction and electromagnetic repulsion are in acceptable balance. There's also a hard limit to how large a nucleus can be. Beyond a certain number of protons, roughly around 120 or so, the electromagnetic repulsion becomes so overwhelming that no arrangement of neutrons can stabilize the nucleus. No matter how many neutrons you pack in to provide additional pion-mediated attraction without adding electromagnetic repulsion, the repulsion between the protons tears the nucleus apart almost instantly. The heaviest element ever synthesized is oganesson, element 118, which has 118 protons in its nucleus. It was first created in 2006 at the Joint Institute for Nuclear Research in Dubna, Russia, by bombarding californium targets with calcium ions accelerated to enormous energies in a particle accelerator. Oganesson nuclei survive for less than a millisecond before decaying through alpha emission, shedding helium nuclei in a chain of decays that steps down through progressively lighter elements. Only a handful of oganesson atoms have ever been produced in the history of science, and their properties are known only approximately from those brief moments of existence. But there's a fascinating wrinkle in this story. Physicists have long predicted that within the super-heavy region, at certain specific combinations of proton and neutron numbers, there might be an island of stability, a cluster of super-heavy nuclei that are unexpectedly more stable than their neighbors. The idea comes from nuclear shell theory, which shows that nucleons inside a nucleus occupy quantum energy levels similar to how electrons occupy energy levels in atoms. Just as atoms with filled electron shells, like helium, neon, and argon, are chemically inert and exceptionally stable, nuclei with filled nucleon shells are especially tightly bound. These filled shell nucleon numbers are called magic numbers. For protons, the known magic numbers are 2, 8, 20, 28, 50, and 82. For neutrons, they're 2, 8, 20, 28, 50, 82, and 126. Nuclei with magic numbers of both protons and neutrons are called doubly magic and are extraordinarily stable. Helium-4 is doubly magic with 2 protons and 2 neutrons. Lead-208 is doubly magic, with 82 protons and 126 neutrons. It's the heaviest stable nucleus with a magic number. Theoretical calculations predict that the next magic numbers beyond the known ones might be around 114 or 120 for protons, and 172 or 184 for neutrons. If nuclei could be created with these magic numbers of protons and neutrons, they might be significantly more stable than surrounding super heavy nuclei. Not stable forever, probably, but stable enough to exist for seconds, minutes, hours, or maybe even years rather than milliseconds. This hypothetical island of stability has driven experimental efforts to synthesize ever heavier elements. Every new element created is one step closer to testing whether the island exists. And the entire theoretical framework predicting the island is built on the same pion-mediated nuclear force we've been discussing. The shell structure of nuclei, the magic numbers, and the enhanced stability at closed shells, all of it arises from the specific properties of the nucleon-nucleon interaction, which is ultimately governed by pion exchange at nuclear distances. Let's step back now and consider the full scope of what the pion makes possible. Every atom in your body that is heavier than hydrogen owes its existence to pion exchange. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood. Every single one of these elements exists because pion exchange between protons and neutrons creates a force strong enough to overcome electromagnetic repulsion and bind nucleons into stable nuclei. Without pions, without the residual strong force they carry, the only element in the universe would be hydrogen. One proton, one electron. No helium, no carbon, no oxygen, no periodic table beyond the first element, no chemistry beyond the simplest reactions between hydrogen atoms. No stars as we know them, because stellar fusion requires nuclei to come together and form heavier elements, a process that depends on the nuclear force to bind the products. No planets, because planets are made of heavy elements forged in stars. No water, because water requires oxygen. No organic molecules, because organic chemistry requires carbon. No life, not a trace. This is the weight that the pion carries. This small, fleeting, unstable particle, living for just 26 nanoseconds in its charged form and 84 attoseconds in its neutral form, is the reason complex matter exists. It is the bridge between the confined quark-gluon world inside nucleons and the nuclear structures that make chemistry and biology possible. It is the carrier of the force that builds the periodic table from hydrogen upward, element by element, nucleon by nucleon. And yet, almost nobody has heard of it. The pion is one of the least famous particles in physics. Ask someone on the street to name a subatomic particle, and they'll say electron, proton, neutron, maybe quark or photon if they're interested in science. Almost no one will say pion. It doesn't feature in popular culture. It doesn't have the mystique of the Higgs boson or the romance of the neutrino. It sits quietly in the physics textbooks, doing its job, holding the nucleus together, making everything possible, and getting almost no recognition for it. There's something fitting about that in a way. The pion is a residual particle, an echo, a leftover effect of a deeper force. It's not fundamental in the way that quarks and gluons are fundamental. It's composite, made of a quark and an antiquark. It's unstable, decaying quickly whenever it exists as a real particle. It's virtually, most of the time, existing only as a fleeting quantum fluctuation during the exchange process. It's modest in every way, small mass compared to protons, short lifetime, no permanent existence outside of nuclei. And yet, take it away, and the universe collapses into a featureless sea of isolated protons and electrons. No structure, no complexity, no possibility of life or thought or wonder. There is a hierarchy in nature that runs from the most fundamental to the most complex. At the bottom are quarks and gluons, bound together by the color force into protons and neutrons. Above them are the pions, the residual messengers that carry the nuclear force between nucleons, binding them into nuclei. Above the nuclei are the atoms, held together by the electromagnetic force between nuclei and electrons. Above the atoms are the molecules, held together by shared electrons in chemical bonds. Above the molecules are the cells, the organisms, the ecosystems, the planets, the stars, the galaxies. Each level depends on the level below it. Each level emerges from the interactions at a smaller scale. And the pion sits near the bottom of this hierarchy, at the critical juncture where the strong force transitions from the confined quark-gluon world to the nuclear world. It's the hinge, the joint, the connection point between the deepest level of matter and the structures that build upward from it. Think about what we've covered tonight. We start with a simple question. Why don't protons in the nucleus fly apart? The answer took us deep into the heart of matter, down to the level of quarks and gluons, through the mechanism of confinement and the seething quantum chaos inside a proton. It brought us the brilliant insight of Hideki Yukawa, who realized that the range of a force reveals the mass of its carrier. It led us through the confusion of the muon, the eventual discovery of the true pion by Cecil Powell, and the detailed mechanism of pion exchange between nucleons. And it brought us to the consequences of that mechanism for the structure of the entire periodic table, the energy of stars, the existence of nuclear fission and fusion, and the possibility of complex matter and life. The particle that holds the nucleus together is the pion, not the gluon, which is confined inside nucleons and cannot escape, not some vague, undefined strong force, but a specific particle, a quark-antiquark pair, exchanged between nucleons as a virtual quantum fluctuation. The pion mediates the residual strong force, the nuclear force, the force that overcomes electromagnetic repulsion and binds protons and neutrons into the nuclei of atoms. It's a secondary effect, a shadow of the deeper color force inside nucleons. But it's the shadow that builds the world. Every atom heavier than hydrogen, every element in the periodic table beyond the first, every star that burns, every planet that forms, every molecule that reacts, every cell that divides, every thought that crosses your mind. All of it depends on pion exchange. All of it traces back to virtual quark-antiquark pairs flickering briefly into existence between neighboring nucleons inside atomic nuclei, carrying a force that lasts for just long enough and reaches just far enough to hold matter together. The next time you look at your hand, or at a tree, or at the night sky full of stars, remember what you've learned tonight. The atoms in everything you see are held together by a particle most people have never heard of. A particle that exists only fleetingly, that carries a force only a femtometer or two, that is nothing more than the faint residual echo of a deeper interaction, locked away inside protons and neutrons. The pion, small, brief, almost invisible in the grand catalogue of physics. And yet, without it, none of this would exist. Not the stars, not the earth, not the air you're breathing, not you. That's the particle that holds the nucleus together. And that's the particle that holds the universe. Together, one nucleus at a time. Thank you for joining me on this journey into the heart of the atom. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the science that shapes our universe. Sleep well tonight, knowing that the atoms in your body are held together by a force that physicists spent decades trying to understand. A force carried by particles most people will never hear about. A force that makes everything possible. Good night.